Hey, myself Robin, and we will solve some of the simple questions of tree today. Let's solve some basic questions today. Let's start with the simplest question with the binary trees. Now we have been given a binary tree, and we need to figure out whether that given tree is height balanced or not. Okay, what is the definition of height balanced binary tree? It is defined as a binary tree in which the depth of two subtrees of every node never differ by more than one. Okay, I need to return 0 or 1 for this problem. I need to return 0 if my tree is not balanced, and I need to return 1 if the given binary tree is balanced. This is the input that is being given to me, and I need to figure out whether the given binary tree is balanced or not. Okay, as we can see that the height of the left subtree here is just 1, as well as the height of right subtree is also equal to 1. It means that, okay, the difference between the heights for the left and right subtree, it's equal to 0. Okay, if it is 0, that means it is less than 1. So the answer for this case, it should be true. Okay, fine, nice. Now if I just visualize this input, in this input, as we can see that in the left side we have two nodes, but in the right side we don't have any node. It means that, okay, the height in the left subtree, it's equal to 2, but the height of the right subtree is 0. So if I take a difference, then the difference for this as a rule, it's equal to 2 minus 0, which is 2. And as it is greater than 1, so that means I need to return false or 0 in this case. Okay, now we got the question. Okay, now let's try to visualize how we can solve this question. Okay, the question is, we have been given a binary tree. Let's say this is the binary tree that is being given to us, and we need to figure out whether that given binary tree is balanced or not. Okay, the simplest thing is kind of a really simple question, that what we can do in this case, I need to first check if that given binary is balanced or not. That means that first of all, the left subtree also should be balanced, as well as right subtree also should be balanced. That should be true. If both the things are true, and if I just calculate the height of the left subtree as well as the height of the right subtree, if I figure out height of both the subtrees, then the difference should be less than equal to. If these three cases are true, that means I can say that, okay, that given tree is height balanced. Okay, now if I need to do that, in order to solve for my complete tree, whether that complete tree is height balanced or not, what I need to do, I need to check for my left subtree whether my left subtree is height balanced or not, or as well as my right subtree is height balanced or not. And again, when I just reached at my left subtree, and again I will check whether the left child of left subtree, the left subtree of the left subtree, it's balanced or not. Similarly, I will check for the right side, and for here as well, I will check for both the sides. So it seems to me kind of a recursive approach, in which the way I can solve this question, if I build some sort of recursion. Okay, I need also some sort of information which will help me to evaluate the height in the left side as well as in the right side. Simplest approach that is coming to my mind is, what I can do, I can make a function, pass the root, and check whether the left side is balanced or not, or also check whether the right side is balanced or not, and somehow evaluate the height for the left side and evaluate the height for the right side as well, and then just check the difference. And if this gives true, and height is less than equal to 1, in that case I will return true, in other case I will return false. If I just apply that algorithm, that will give me the answer. But now let's try to analyze the complexity of it. Okay, I'm doing some sort of one traversal over the tree, which will cover my recursion part, and also I'm evaluating the heights. Okay, if I will evaluate the height, that means if I am at some node, I need to traverse each level if I want to figure out the height of the given tree. Okay, again, that can go up to order of n. And at each step, I am just figuring out the height. So the complexity in if I solve by this algorithm will be order of n square. Okay, can I do better? Okay, if I want to do better, that means I want to somehow pre-store the height information. Okay, so one approach that is coming to my mind that what we can do, first evaluate the height of every node. Okay, but then it will take off an extra space. Okay, though, so two solutions comes to us. One of them gives us solves our question in order of n time, order of n square time, and order of one space. And the other solution solves our question in order of n time and order of n space. Can we think of something better? Okay, such that we can solve this question in order of n time and order of one space. Okay, let's try to think first. Okay, the point is just we need to check one thing only, and that thing is basically the difference between the heights of left and right subtrees. Okay, and if I check this information at each level and at for each node, and each node just give me the answer, the difference less than equal to 2, then I am damn sure that that given tree is height balanced. So but one thing that is coming to my mind, that forget about this thing, just try to solve in such a way I can just figure out the heights, because I know that if I want to figure out the height of a tree, it will be I need to figure out the height of my left subtree as well as I need to figure out the height of my right subtree. So if that is the case, and the height of this will be, because anyways if I want to calculate the height of a tree, I want to evaluate the height of the left and right subtrees. So the whole recursion part, it can also be covered here. So one thing that I can do, I just evaluate the height of every node, because if I want to evaluate the height of every node, I am checking this condition. I'm doing this thing. So, and I can check whether the difference is less than equal to 1. If it is, that means I'm done. That means, okay, if it is greater than 1, that means I just found a node such that that node is not height balanced. If a particular subtree of a given tree is not height balanced, that means I can't say that the whole tree is height balanced. That means the whole tree is also not height balanced. Fine. So I can, the one thing that is coming to my mind, that what I can do, I can keep a one global variable which just track this information. And if I just solve in that way, I'm done. Sounds like a good solution. Okay, let's try to solve this now. So the way I think is, so let's first make a global variable is complete tree balanced, and I can initialize the value here for this global variable. It's complete tree height balanced, and I should initialize it with true. Okay, now what I can do, I can calculate the heights for each node, because I know that while I'm calculating the height, I can check the overall height balancing thing. Let's calculate the heights. Let's say first for A, and it should return me integer value. So let's calculate height for a given tree node. This is the case. Now if A, let's try to handle the H case. If we don't have A, then I need to return 0. Otherwise, the left subtree height, if I need to evaluate, then I need to calculate left height. Again, that function with the left node. If I want to evaluate right subtree height, same function with the right side. I need to follow this procedure, and now I can check this thing. If the difference between left subtree height and right subtree height is less than equal, is greater than 1, that means I'm done. I just found a node or I found a subtree in more specific sense that is not balanced. So I can change my global variable is complete tree height balance or not to value false. Nice. If I do in that way, I can surely achieve something. And I need to return the height of that given tree, which will be equal to max of left subtree height or right subtree height plus 1. Nice. If I just solve in that case, and I can return that global variable, because if it is true, I need to return integer. I just need to check if it's complete tree height balanced. I need to return 1, else I need to return 0. That is it. Let me check. I just created a global variable is complete tree height balanced. Okay, now I'm checking the height, calculating the height. The left subtree height is I'm calling the same recursive function again. And for calculating the right subtree height, again I'm calling the same recursive function again. Now I am checking whether if the difference between the left subtree height and right subtree height is greater than 1, then means I am just updating my variable. Otherwise, I'm returning the max of left subtree height and plus 1, adding 1 to it, and I'm initializing it with true, and I'm calculating my height, and I'm done. Nice. Let's submit my code. Nice. Oh, we already got 261 points. Nice. Let's solve some other question. Okay, he said you took some basic question. Okay, let's try to solve some good question. Let's pick this one. Okay, I don't know, but this, okay. Okay, given the in-order traversal of a Cartesian tree, and we need to construct that tree. Okay, what is Cartesian tree basically? Cartesian tree, it's basically a heap ordered binary tree where the root is greater than all the elements in the subtree. Okay, you may assume that duplicates do not exist in the tree. Okay, nice. So the thing is, we have been given a Cartesian tree, and he cleared me the definition of Cartesian tree as Cartesian tree is basically a heap ordered binary tree. Okay, if it is heap, that means whether the root contain the maximum value of the given tree or it will contain the minimum of the given tree, and it says that the root is greater than all the elements in the subtree. That means root maintains the information that is the maximum value of that given tree. So I need to construct a tree, or I have been given in order traversal of the game. Okay, if somebody, or if most of you who don't know about Cartesian tree, let me briefly tell what the Cartesian tree is and all those things. Cartesian tree, it's basically the concept Cartesian tree comes because the thing is it's a kind of BST plus heap, or in some sense we can also call this tree as tree. And the way we have the definition that we have been given a Cartesian tree in that form. That is we have been given the in order part of it, because we know that if the given tree is BST, we can, if we have been given some order, with the some specific in order. Let's say that in order is 1 2 3 4. We can construct so many binary search trees. One of the binary search tree that we can construct is simply 1 2 3 4, because in that given binary search tree, the in order is 1 2 3 4, and with the same in order we can construct so many binary search trees. The point is, so the way Cartesian tree comes, it just gives us the unique binary search tree, and that uniqueness comes because of that heap part. Because in that case, why that heap thing helps me, because the way heap we design the tree now, such that the root contains the maximum value and it also maintains the in order part. That's the basic property of BST. Okay, let's say we have been given a tree 1, 2, 3, 4. Let's say the maximum value is 4. So I can say that, okay, the 4 should come as a root, and the elements, let's say the elements before, after 4 are, let's say the elements are 3.7, 2.8, something like that, and that is the in order. I know that that is the maximum value. That means that, and I need to maintain in order as well. So it means that all the nodes which are less, which has having a index less than 4, that means all these nodes should come into the left subtree. Why? Because I need to maintain in order. I know that the in order of a BST is left, root, right. If that is the case, that I know that the in order is left, root, right, it means that, okay, first I need to evaluate left and then root and then right. So I can say that the all the nodes after this node will definitely go into the right side, and all the nodes before this node will definitely go into the left side. So we have been given the in order of a tree, and the heap is kind of a max heap. We need to construct that tree. That is our question. The question is quite simple. Okay, let's try to first construct a tree. This question is also not too complex. The point is, we have been given the in order of the given tree in the form of an array. Okay, and I need to construct the tree. Fine. Okay, in this question as well, I can just somehow apply some sort of recursive approach, and in that recursive approach, what I can do, first of all, I have been given a complete vector. What I can do, I just figured out the maximum value in it. I just figured out let's say I just figured out the maximum value in it, maximum value in that complete vector, and I just make it as root. And now what I can do, I can just now recursively call for the left side as well as recursively call for the right side. And now what I can do, I can just construct this as a tree as well, and I can mark the left child for this root as the root of the left subtree, and I mark the right child of that node as the root of the right subtree. If I just solve in that way, then I can solve this question. Now, first, before jumping into the code, let's first try to analyze the complexity for this question. Okay, first, what I am doing, I am just calculating the maximum value. At each instance, I am calculating the maximum value. Okay, I'm calculating the maximum value, which is of kind of order n, and I'm calculating the maximum value at each step. Let's say I have a function which gives the root, so it has a node which gives me the root of the tree when it takes a given array. Now what I need to do, first I need to find the maximum element in that given array, and then I need to call the recursive function again. Let's say the index I just got after calculating the maximum value from that given array, it's, let's say, I. So I need to call the function from the left side to the I minus 1, and that same function again with the I plus 1 to right, because this should go into the right side and this will go into the left side. And what I can do, I can mark the left as this and right as this, and I can return this. Now the complexity is the order of n, just because I am traversing over each of the node, over each element of the array, and also I am figuring out the maximum value in that array as well. So the overall complexity for this solution, it will go up to order of n square. Okay, so we just figured out the solution which is of order n square. Now the point is, can we solve it in a better way? That is the point. Can we solve it in a better way? One thing we just figured out that what we are doing, we are just concerned about the maximum value. Okay, and somehow I know that if that is the maximum value, and so all the nodes here are comes to the left side of it. Okay, let's say I have a sequence. Let's see the sequence. Let's see the example. Let's say we have a given sequence as 5, 4, 8, 3, 1. Okay, if we have that given sequence, what we can do now? As we can see now that we have a 5, and if we just found an element which is lesser than this element. So I can safely say that as 5 is greater than 4, that means the 4 should go to the right side of it, for sure. Okay, now if I figured out 8, now can I say anything if I figured out 8? Now I know that, okay, if I have some elements, let's now try to construct something such that we can able to solve our question in less complexity or better complexity. Now let's try to think what we can do to solve our question in a better complexity. Okay, the thing is, let's say I have 5, nice, then I come across 4. If I come across 4, I know that 4 is less than 5. That means what I need to do, I need to make it as a right child of 5, for sure. Let's say I just do that operations as well. Let's say I just keep it as right child. Now, okay, do I need the information of 4 ahead? Will it help me in any further processing? Okay, I don't know. Let's see. Let's say I just found a value 8. If I found a value, let's say now 3. After 4, let's say I found a value 3. Now what I can do? Okay, if I found a value 3 and I know that 3 is less than 4 and 3 has a greater index. That means 3 will go into the right side of it. Okay, so I just figured out a solution. If we have been given an in order in such way, then I just need to map as a kind of right child of that particular node. Okay, if that is the case, then I'm happy. If so, that means I'm just keeping the information and the time I'm getting the value, which is less than the particular value, in that case, I just need to mark it as the right child. Fine. If that is not the case, let's say I'm just getting a value which is greater than this value. Let's say I'm getting a value which is 4.8. Now, so that means what should be my structure now if this information is given? If this information is given, then I know that, okay, let's say we have 5. I know that all the elements, these are less than, the elements I am storing here, it's kind of in reverse sorted order. So if it is greater than 3, nice. So that means all these nodes should go into the left subtree of this, because I need to maintain a heap kind of information. So this particular node should be the root for these two nodes, for sure. So what I can do now, the overall structure at the end, it will be something like 5, then the right child 4.8 will come, and in the left subtree I will have 4, and I know that structure. So what I need to do now, what I am just doing now, if I am getting a value which is, let's say I am iterating over the array, if I am getting a value which is less than that particular element, then I am just making that node as a right child of it and just push that something. And if I am getting a value which is greater than this thing, then I just pop all the elements which is in this stack or some data structure, because I just said stack because it is following that property. Why? Because what we are doing, we are adding the elements in the end as well as we are removing the elements from the end. And if we follow the same procedure, somehow we will able to achieve our solution, isn't it? Does it sound good to everyone? The way I'm approaching or the way I'm dealing this problem, if I want to achieve it in a better complexity. So the point is, if we follow the same way, we can now the complexity. Now let's try to think about the complexity. If we just try to solve in that way, the thing is, what we are doing, we are just inserting an element in the stack. If that element is lesser than the topmost element of the stack, and I'm marking it as right child of the topmost element, fine. Otherwise, if the given element that I just encountered, it's greater than the topmost element of the stack, then what I need to do, I just need to pop out some of the elements from my stack. Let's say I just popped out these two elements in that case. So the last element which I popped out, I need to keep track of that information about the last element. And I need to make the left child of that particular node as that particular element. And now the topmost element which is present in this stack, I should make that particular node as the right child of that particular node as 4.8. Because in the end my structure should be something like this, isn't it? If my structure is something like this, only then I can say that that is maintaining some sort of heap information as well as maintaining in order as well. So if I will solve in that way, I can solve my question from order of n square to order of n. Nice. And we know that we can't solve better than this complexity. This is the best complexity that we can achieve for this particular question. Now let's try to solve this question. So as I just told you, we need a stack to maintain all this information. Let's say I created an empty stack, and okay, now let's iterate over my entire array. Let's first keep n as size. Now what I can do, as I know that, okay, let's first check the big edge cases. Let's say if my stack is empty. If my stack is empty, that means I don't have any elements in my current stack. That means that the particular element should be the root. Or if that is the case, or okay, let's first create a root. So that means in that case, let's say my root will be new tree node, and I have been provided a constructor in which I can just pass the value of integer and it will create a node. So I just need that value, which is a of I. Nice. And kind of I'm done. Okay, now I figured out the root, and it's better to maintain a stack of tree node. So I can push into my stack, the value of root. Fine. Now the point is, now the case is something like I have an element in the stack, but the current element that I figured out, it is less than the topmost element of the stack. The topmost element of the stack, and I need to just concern about the value of that particular element. So because I am adding the basically nodes into this stack. Now if I just do in that way, in that case, what I need to do, first of all, let me create a new node. Okay, with the value ai, and mark the right child of the topmost element of the stack as that given node, and I can push that given node into the stack. Fine. Okay, even if that is not the case, that in other case, the other case is I have a value that means ai is greater than the topmost value of the stack. Then in that case, I need to pop out some elements, and I need to just concerned about the edge case as well. If my stack is not empty and the value at the top, it's basically less than ai, we are happy because we don't have given any duplicates in the tree. So we can do in that way. We shouldn't have to handle the duplicacy case here. So we are good with that. Now, if that is the case, then what I just told you, then I need to keep track of the last element which gets popped out, because that last element will be the left child of that particular element of ai, isn't it? So if that is the case, then I can make last, and I can update my last as Toto, and I can remove I can keep it as null. Okay, now what I can do, I just figured out the last element. So let's first create a new tree node for that particular element. With the value of ai. Now what I can do, the value for that particular node, the left child of that particular node will be my last, and the right child for the topmost element. If let's first check whether we have a topmost element in the stack, or there might be a case that my stack gets empty. So I need to check that thing. If my stack is not empty, then but I need to check whether the I need to mark the rightmost child for the top as the given one. If I just do in that way, I will somehow solve this question. Looks like a good approach to me. And I need to return true. Let's again check the way we think and the way we applied the algorithm. Are they both matching or not? Or have we missed any case or not? Let's first check. Okay, what we do in the starting, we just created a stack and which contains all the nodes. Nice. And we just take our n, which is the size of my array. Nice. I just iterating over my array and I'm just checking whether my stack is empty. Because I know that stack will be empty, only in that case, I need to push now that element as well. Sorry. I just forgot that thing. Okay. Because if that stack is empty, that means this is the first node, kind of. So that means I need to make it as a okay. Oh, sorry. I just need to push. Okay. Okay. So that means I can't say that it will be my root. The root must be the topmost element in this stack for sure. But yeah, I need to construct a node here and I just need to add the node if stack is empty because I can't do anything else. And the other case will be if we have our value, it is less than the topmost value, then we are sure that in that case, we need to mark it as our right child for that particular element. So we are doing this thing. So it seems right to me. Now the other case will be if AI is less, if it's not less than, it will be greater. So that means it should be the root of some of the nodes. So I'm just checking out all the nodes. So for that, what I'm doing, I'm just checking up till when I have that given value, it's greater than to the topmost value. So I'm just maintaining my last node because it is required. And what I am doing, I am just creating one new node and just what I'm doing and just mark the left child for that particular node as a last. Nice. If I do in that way, it seems like a good thing. Now let me test. Okay. Oh, sorry. Nice. Let's submit this code. Oh, okay. What's wrong? Let's try to see. Have we done anything wrong here? We have been given the tree as 231. If we have been given tree as 231, first what we can do, what we are inserting 2 here, and it shouldn't be that. It will be the first element. It shouldn't be the last element of this stack. Okay, so I need to maintain the last information. Let's say it as null. Because the way we are maintaining our stack, it's in reverse sorted order. If it is in reverse sorted order, what does it mean? That means the maximum value should come in the front of my stack. And I am popping the element in that a way that if we have a maximum element, it won't be go out of my stack. And it will always be appear in the starting of my stack. So I need to update as this and I need to pop. If I do in that way, then it should work. Oh, sorry. Why now? I'm updating my last here. Okay, it's not stacking. Sorry, I'm doing some silly mistakes today. Let's check. Nice, we solved this question. It took us some time, but we solved this question in order of n time. That's good. That's good for us. Okay, let's solve one more question today. Let's solve this question. I don't know what's this. Okay, the question is we have been given 2 binary trees and we need to check whether they are equal or not. Okay, 2 binary trees are considered equal if they are structurally identical and the nodes have the same value. Okay, I need to return 0 or 1 depending upon this. Okay, let's say I have been given this tree and this tree. I just need to check whether those both of the trees are equal or not. It's kind of a very simple problem, but I need to check if the both of the trees are equal. That means there the node itself will be equal, as well as the left subtree and right subtree, both all of them, both left subtree and right subtree also should be equal. If all those things are fine, then I can safely say that the both of the trees are identical. To solve this question, it shouldn't take much time. Then what I can just first concerned about the edge case, and you can see that this question, this simple question, it's been asked in Amazon as well. So, but the point is, are we handling all the edge cases? Are we come up with a good solution at one go or not? So, what are the edge cases? What will be the edge cases in this question? The basic edge case for this question will be kind of, let's check whether we have been given both the nodes as empty or not. If we have both as empty, both the trees as empty tree, then I can safely return 1. Because I know that in that case, both of the tree are identical. If any of them, if both are not kind of empty, one of them is empty, that means both the trees are not identical. And in that case, I need to return 0. So this will be kind of the one more edge case. Now I end up with both the trees such that both the trees has some elements. Now in that case, the idea is very simple, but I need to check whether the basically value for both of them are equal or not. And it is equal, and I say that if the left subtree for both the nodes, are they equal or not? Oh, sorry. I need to concern about the left subtree only. And also we need to check whether the right subtree for both the nodes, are they equal or not? If all these three conditions met, then only I can say that both the given tree is identical. Otherwise, both the given trees are not identical. If I just solve in that way, I am done. Sounds like a simple solution to me. Okay. Oh, sorry. Today I'm doing a lot of silly mistakes. Nice. Let's submit our code now. Nice. We got a really good point. गोयल दोनों नॉन नल होने से ट्रू कैसे कह सकते हैं? I didn't say that, Goel. What I just said to you that basically, if both of them are null, only then we are saying that as true. Because in that case, both of the trees are empty. If both of them are non-null, then I am checking. Then I'm checking all the three conditions. Now, where the first condition is whether the value of the nodes are equal or not. If both the trees needs to be identical, okay, fine. Thanks everyone.